All right, so the only announcement will be written test 2 tomorrow, okay, during your enroll lab session. 15 minutes, everything will be just like the last time for the written test. Please come in time, and then I will guide you into the room when ready, okay. Any questions in general about the course?
Yeah, for tomorrow's written exam, what is the scope of it? What is which slide number?
I believe I said 58, I believe. I could be wrong.
I think it's 58.
Yeah, 58, yeah.
Guard strength, right?
Guard strengthening, yes. Yeah. But today, I just want to talk a little bit, I want to recap for everybody. It could be like a review, right? Just to revisit some concept about guard strengthening. And then I also want to just do a little bit new stuff about invariant preservation. That one does take a little bit of explanation as well. I want to do that. If that's the only thing I want to really talk about. If I can finish earlier, I can stop the recording, and then you guys can come in front if you got any question for me. I can stay longer if needed. Okay? Anyway, we'll see. Question, sorry.
Sorry, on the lecture slides, there's the bridge controller, it goes up to 94, but there's a guard strengthening stuff after slide 58. Right? What on that slide shows?
I don't think so. Maybe the guard strengthening you're talking about after 58, maybe that's the one in M2, in the refinement number 2. That's a different consideration. You don't need to worry. Because for that one, you also need to understand different guards, different events. So don't need to worry. Yeah, only up to and including 58. Good.
Just up until Thursday's lecture?
That's correct. Yeah. So today, I just want to do a little bit recap. I want to revisit about the intuitive idea about guard strengthening. So hopefully that can help. And then we'll talk a little bit about invariant preservation as well. Okay, good. Yeah.
Since you're recording, can you clarify? Because in your review recording that you share with us, you already clarified, but you're still keeping the same answer for one of the review questions, the n equal 10, which is not supposed to be there.
Mm-hmm. Okay, yeah. I did realize that one definitely is more like a typo. I kind of fixed that in the like a practice test. Okay, anyway. So when you were doing the practice test, let's say you want to put in the init, let's say, and then of course you have the action part, begin, and also you got the end right here, okay? And one of the options is n equals 10. Apparently that one is not valid, because to be a valid action, you have to say, for example, the valid way to say that would be n becomes 10, apparently, right? So n equals 10 should not be a correct option. Maybe I really meant to type it as n colon equal 10. But anyway, I fixed that already for the grading, so you don't need to worry. So hopefully that's clarified?
Yeah.
Okay, good, yeah. Of course, to be an action, you definitely cannot actually put equals. That one is more like a predicate, right? Good, okay, good. Let's now do a recap from our last time. And then I want to revisit about guard strengthening, which is really important, okay? All right, so let's now talk about, okay, first refinements. We talk about ML out and ML in. So these two events already exist in the abstract model M0. So these two are the concrete version that we have over here. And they are kind of defined in terms of A, B, and C, right? The concrete variables. And we spoke about how we can derive the guards, the concrete guard over here, right? We talk about these two, and also this one over here. We also gave you a little bit of exercise. I think quite a good number of you already showed me your answer. So why A equals 0 is not strictly necessary. To really show that, you can want to show that the existing guard combined with the existing invariance is going to entail this particular guard. So that means that one is more like a theorem that can be derived by the existing guard and the invariance. Okay, so you don't really need to put that. That's why you don't see that on the slides in the final version. And then we talk about state transition. That one's pretty easy. I'm going to also make it a little bit more general today. You can think about whenever you're doing some transition using the concrete version of the events, there should be a corresponding one in the abstract over here. So ML in the concrete should really correspond to the ML in the abstract. We call this simulation. It's more like a special term, which I'm going to talk to you about a little bit later today. Okay? So just remember, you got inits over here. And also, every corresponding state between the abstract and concrete, they should be related by the linking variance. In this case, A plus B plus C equals N, right? That's what we have. Okay. And then we got the before-after predicate right here. So the idea would be, so here, if you only mention one variable, Hello? Hello? Guys, please, one more warning. No more. Thank you. So here we got, here we only mentioned about C here. But what about A and B? Anything you don't really mention here, that means they don't really change their value. So you got A and B here, simply don't change their value. All right? So before, after predicate. And when we talk about later about invariant preservation, we will actually have to use the before, after predicate again. So we'll do that exercise together. Okay? Okay, so we talk about abstract versus concrete. So anything in M0 is considered abstract. You got abstract variables, you got abstract events, and also abstract guard. Everything in one is concrete. Okay. And then just formal notation. You don't really need to memorize them. You just got to make sure you can use this as a reference guide. When you look at the corresponding, for example, proof obligation rule, you would know how to refer to them. I wouldn't really just ask you about what does V really denotes. That's not the kind of question I would ask. However, you do have to know what's the corresponding proof obligation for guard strengthening, for example, right? That one's covered. Right? But for the exam, when you craft your data sheets, you can also feel free to actually put the various proof obligation rule on the sheets. Of course, in that case, you have to remember, what each component really means. Or you can just put an informative, like an intuitive version, which I also had in the slides. It's kind of up to you, right? Okay, and then, okay, very important page about the predicates being weaker or stronger. Whenever we talk about two predicates, you want to say one is actually weaker, the other one is stronger, right? As long as you can show there's an implication relation between them. If you can somehow show or prove that P implies Q. In this case, P on the left-hand side is said to be stronger, and Q on the right-hand side is said to be weaker, all right? And if you want to visualize it, think about P here is going to allow certain set of values, and Q is going to allow another set of values. In that case, the stronger one is going to be a little bit stronger in filtering out the values. So that means the stronger one is going to be a smaller set, and the weaker one is going to be a little bit weaker in filtering out the values, or it can allow more values to be included in a set. So this is stronger one, this is a weaker one. So you can go either way. If you just want to go to the pure logical approach, just try to think about the implication. Or if you want to visualize about which set is bigger, you can go that way too. Right? So we did an example right here. And in our particular context, which I'm going to redraw very soon, you can think about the strongest set should be the guard in the concrete model. And the bigger one, the weaker one, should be the guard in the abstract model. Okay, I'll get into it a little bit more. Okay. Any question about stronger versus weaker? Good. Question. Oh, that one just define S. Yeah, may not be standard, but I think maybe some mathematician will use it. So you talk about these two symbols, right? It's just like a define S. Like that. Okay, good? Good. All right, let's talk about this one here, guard strengthening. Okay. So what we said last time, maybe for that part I wouldn't repeat. For that part, we are basically saying G implies H, which means the abstract here is stronger, but the concrete here is weaker. That one is the wrong version. I was trying to kind of explain by saying why this is wrong. Okay? You can revisit that part there. That one I wouldn't repeat, but I'm going to talk about another angle. Let's explain the correct version to see if there's any insight you can actually gain. But the bottom line, the principle, the refinement behavior should be somehow consistent with the abstract model, meaning that the concrete version should not create any new behavior. That means there should not be any scenario where the abstract guard is disabled, but somehow the concrete guard in the same state will be enabled. In that way, the event in the concrete world can just happen. That means you got some new behavior over there. Okay, we'll see. I'll give you an example. Okay, so, and then that's the proof obligation rule right here. Okay, so that one there I'll relate to you. It's pretty straightforward. You just have to realize it's actually like the concrete implies the abstract. And one of your fellow students also pointed out this I here is actually index, meaning that the abstract guard itself may contain several parts. In here, we only got one part, just n less than d, hypothetically. If we got n less than d, maybe another guard over here. We got two guards in total. That means We have to prove each one of them one by one. You got to prove one here as the goal. You got to have another one as a separate sequence. You got to prove them separately. Okay? Pretty much like an invariance, right? When we want to prove about the preservation of the invariance, we're going to prove invariant by invariance rather than all the invariants collectively. Okay. All right. Okay, so your written test 2 will be up until slide 58. Right? Question so far? Okay, let's get back to that guard strengthening intuition. Okay, let's do that. Right here. Okay. Again, let's now revisit that. And I'll try to explain in a slightly different angle, but it's still consistent. So we talk about, again, refinements. And then we talk about guard strengthening. Okay, over here. So the correct version should be the concrete guard implies the abstract guard. H implies G. Okay, let's make some annotation right away for us. This is a concrete guard. And this one here is the abstract guard. And let's make one example right away. Okay, so let's take our example from before. So let's say here, let's get the abstract version. I'll put it in green just to be consistent. So let's talk about ML out. Okay, you can look it up. Somehow I happen to remember. So we got N strictly less than D. That's a guard. Okay? So this is really the G, abstract guard. All right, that's the M0. Okay, just part of it. I just show you the part about the events and the guard, M0. And then we know the refinements we have is, put in red, the concrete version right here. That one there, A plus B less than D. Right? And of course, over there, to really make sense out of the concrete guard, which is H, we also get the a relevant constraint, like invariance A plus B plus C equals 0, equals N, and also C equals 0, right? So that's the context. But you can look up the information. It's all on the slides or on the notes. Okay? So this is the abstract guard. This is the concrete guard. At the moment, we do have H implies G. Actually, they are just equivalent because we just did some substitution, right, back last Thursday. Okay? However, if I try something here, hypothetically, if I do, I will change this to less than or equal to. Now, question for you. Is this going to fail the guard strengthening proof obligation? It is going to fail, okay? How do we tell formally, right? So now the question is, do we still have guard strengthening? To answer that question, you basically want to ask. So here you got A plus B less than or equal to D, right? That's a hypothetical change I proposed. Does that imply N less than D, right? You can think about here, A plus B somehow is simply equal to just N, right? You can see C equals 0, cancel out, A plus B equals N. So I can replace A plus B just by N. I'm doing the replacement already. So I'm really asking N less than or equal to D, does it imply N less than D? Not really. You can see that obviously, right? So what does that mean? Let's go a little bit further. So this is not valid, but why? What it really implies to us is we have some new behavior that somehow is introduced at a refined level, which is not acceptable. So this is saying, in the concrete model, in M1, ML out is enabled when N is exactly equal to D. meaning that when the number of cars in the island compound bridge already reached the maximum, we still allow one more car to come in. That's going to violate the cap size, right? But in the concrete one, this one here is still allowed because we say less than or equal to D, right? So it's still enabled. But it is disabled in M0. So in the same input scenario where n is equal to 0, the behavior for the M0 abstract one is it should be disabled. However, we are creating a new behavior in M1. That one there is going to make it enabled, inconsistent. All right? So this is telling us the guard strengthening is not being satisfied. So that means the implication sign should really hold always. Okay? Let me recap, just in case. Okay? So this is not just relevant to your written test too, actually. So this is just in general understanding about guard strengthening and maybe in preparation for the exam. Let me say that again. The correct version goes like this. We got n less than d, a plus b less than d. This one here, we can somehow show that this concrete guard implies the abstract guard. So that is good. I make a small change by changing this less sign into less than equal to. That's a new concrete guard. But this concrete guard here is no longer stronger than the abstract guard. I cannot really show the implication because there's one value there. Okay? So let me just put it down again. So if I put it here. So think about right here. So what we have is this one, we're supposed to have H implies G. But here we got G actually and H actually got reversed over here. So there is one value over there that is going to be satisfied by H, but not G. This is when N is equal to D. So think about this diagram here and draw a connection to about a predicate being stronger or weaker. Okay? Okay, having this said, let's now think about this one here and then make some annotation. Okay? So the way to visualize this is, let's think about concrete guard is going to be smaller, is the stronger one. Okay? So that is H. Let's put M0 here, just easier for you to see. That's the, I beg your pardon. That's from H1, M1. Okay, M1. And then we have the weaker one, the abstract one, right here. And then this is G, and that is from the abstract. That's the correct version. Okay? Let's try to understand exactly what this diagram can show to us. Okay? And then you can think about right here, think about this is the rest of the condition. Okay? You can think about this condition here. This is simply H. This is like a H and G are both satisfied. Here is H but not H but G. Right? Not H but G. Agree? And also, what about the rest? Neither of them is actually true. It's not H and not G, logically. Right? Let's try to interpret each one of them, so just for you to see. Let's start with the first one. What does this really mean? Okay, this one here is saying, how about this? I'll put a star. Okay, this one here is saying, what is enabled in the concrete is also enabled in the abstract, which means they are consistent. They're just enabled in this particular scenario. Okay, that one is actually not too difficult, but let's look at this one here. That one there, let's use purple. Okay, this one here. This one is saying somehow this what used to be allowed by the abstract, it does not allow anymore in a concrete. But that one is okay. We are just, let me put it down first, and then I'll explain to you. some scenario allowed by M0 is not allowed, which means disabled, by M1. And this is completely okay because we're just saying what used to be okay for abstract, we just don't allow it anymore in the concrete. So we are not really changing the behavior. We're not adding any new scenarios where it can just happen in the concrete. Okay? Still okay because no new scenario created by N1. All right. All right, finally, you can think about right here. How about this one here? This one here, we can look at that a little bit more closely. Think about right here, contrapositive, right? Remember what we learned from the math review? This one is equivalent to not G implies not H. Whatever that is not allowed for the abstract, you should not be allowed as well in the concrete. We just don't allow something that's not allowed in the abstract. Okay? Was not allowed by M0 is also not allowed by M1. Okay? So there, once you draw the diagram, think about what each area really means. That can kind of help you to explain the guard strengthening. But overall, you just want to remember the concrete guard should really imply the abstract guard. Okay? Question?
So does H have to be stronger, or can it just be stronger or equivalent to? Because in this case, D is less than D, and then A plus B is...
Very good question. So here we only require, very good question. We only require that H implies G. That's necessary. Whether or not G also implies H, it's okay if that also implies as well. In which case, they're both equivalent, which is the case actually for right here, because we got strictly less than, right? So you got to make sure at least this is the case. Once this is the case, the other one, we don't care. Yeah. Okay. So this might take a little bit more thoughts, but try to see how much you can digest. Questions? Okay, so that's really all I want to say about guard strengthening. So I think the most important thing is really to understand about the direction. Just remember the concrete must imply the abstract, okay, and also understand the scenario. Not really this Thursday, but next Tuesday or Thursday, we're going to talk about something called relative deadlock freedom. And we're going to look at these guys again. Okay, that could be some confusing part that's going to come. But for now, you don't need to worry. I'm going to want to give some heads up. Okay. Good. Okay, so let's now move on. Right. So these two proofs, okay, I think maybe in the interest of time, I think I'll just leave you guys to really give a try on these proof. Hopefully you already went through them. Also, some of you already dropped by my office hour to clarify certain steps. I'll leave them to you. But if you really want me to go over certain proofs by you, feel free. We can do that. But just maybe not today. But if I can finish the lecture earlier, you can feel free to come to me. We can go over certain steps together. I want to just jump directly to invariant preservation. Okay. So that one there is going to be on slide number 59, right here. Right. So starting from now, it's not on the written test too. You can relax. Okay. So if you just get as much as you can, conceptually nothing much new really. I just want to draw the connection between the two models. Okay. Starting from 59. Okay. But let's now just go over some pages. It's more efficient. Now we want to actually prove about invariant preservation. Specifically, you can see we got ML out, abstract version, ML out, concrete version, ML in, abstract version, ML in, concrete version. We want to do something very similar to when we were back in M0. We want to make sure ML out can preserve the invariance. ML in can also preserve the invariant. That's what you study, right, for written test number 2. But now we want to extend the context a little bit. We want to say, we got the concrete version for ML out, the concrete version for ML in. Do they also preserve the invariance that we added right here? We want to show that, all right? Let's now look at the proof obligation, first of all, okay? Let's now annotate them, okay? So what we have is, let's see here. Let me start with, okay, A here, axiom, right? Hopefully by now you already see capital A always axiom. Okay, we're gonna also do some example together as well. And also we got invariance. But here you can see we got I and J, right? Do you remember the difference? Well, actually, even if you forget, you can see I here and J here. J can actually use more variables than I. The concrete model can always use the abstract variable as well. So in that way, you can also tell. J here really means the concrete one, just in case you forgot. J means the concrete. Okay. So what we have is right here. So I here is the abstract invariance. And J here is a concrete invariance. That one there is a concrete invariance. And then, since now we're talking about the individual concrete event should really preserve the invariance. So H here should be the concrete guard. Now we are already not really talking about guard strengthening. Okay. So that one there is going to be right here. This one here. So this is a concrete guard. Okay. For example, you can see the concrete guard right here, and also the concrete guard right here, right there. All right. Okay. Let's look at the consequence as well. What do we want to prove? And this one here, let me put in pink. Well, this one here basically is using the abstract and concrete variables. So that must be a concrete invariance, but it's being indexed. That means we want to put individual one into it, right? So we're going to prove that this is maintained, this is maintained, this is maintained, and etc. So we got 5 different concrete invariants, and we want to show that ML out can preserve each one of them. ML in can also preserve each one of them. In total, we got 10, 2 times 5, right? So that's something, let's be clear first. So we got 2 concrete events multiply 5 concrete invariants. So total 10 proof obligations. Okay, that's what we have. Okay, I'll put it on the side. Right here. Okay. So let's now try to work them out. Let me only talk about 2 of them, because that's the 2 actually show you the proof on the slides. But I can also try to prove other things as well, especially to prove about A natural number, B natural number, C natural number. They are quite easy to actually show. Right? I'll leave that. You can also give a try. Okay, let's try these 2 invariants specifically. Okay, let's go with the naming convention. Oh, just for this one here. Think about here. Oh, that's important to say. This is the concrete invariance satisfied in the post states. If you recall, when we talk about preservation, in the pre-states, we have the event executed. In the post state, the invariant should be preserved, right? So we talk about the concrete invariant should be preserved in the post states. And these 2, I and J right here, they are about the concrete and abstract event are preserved, are actually are the case. They hold in the pre-states. Okay, right here. Right, let's now talk about 2 of them. Okay, I'll give you the name and then we can work out exactly how to write them. They share quite a lot in common. So let's start with ML out. And then I want to preserve invariance 1, 4. And then that's about invariant preservation. Okay, that's the first one. Okay. And the second one will be, let's say for ML in. And I want to preserve invariant 1, 5, the safety invariance, and then invariance right here. Right, as you can see, one of them is about ML out. The other one is about ML in. And one of them is about invariant 4. The other one is about invariant 5. Right? To give you 2 examples. There should be 10 in total. But these 2 arguably might be the more sophisticated ones. Let's now try to write them out. Exactly. Okay, let's do that exercise, which could be useful for tomorrow or at the exam, right? Later. Let me just try to see if I can just make it a little bit smaller. Okay, good. Okay. So all of them are going to share this part. Oh, sorry. This part here is going to be shared between these 2. Only the concrete guard is going to be different. For ML out, it's going to be this. ML in is going to be this. Right? So let's now write down these 3 parts first because they will be shared in common. Okay? Let's start with the axiom. For axiom, it's going to be, sorry, I don't have it here. Okay, I remember that. So D is a natural number, and also D larger than 0. Similarly, we got the same. D a natural number, and also D larger than 0. Okay, the same. They want to share. And also we got abstract invariance, which will be right here. N natural number, n less than or equal to D. N natural number, n less than or equal to D. And then we got concrete invariance. Concrete invariance, all of them. So that one there is going to be right here, all of them. All right, we have no choice. Let's write it down. So we got A natural number, B natural number, C natural number. A plus B plus C equals N. A equals 0 or C equals 0. In the exam, you will be given a booklet, so you better write each one of them in a single line, right? For now, I just don't have space. I put it in a single line, right? And that one there, I think I might just be able to copy. There we go. Okay? And then this is the part. They're going to be different, right? Concrete guard. One is for ML out, the other one is for ML in. So let's now ML out right here. A plus B less than D, and also C equals 0. And this one here for ML in, right here. C larger than 0. Okay? That's about all the hypotheses you can use. And then we have turnstile. Turnstile. And we got something here. Something here. Okay? Hopefully so far so good, right? And for the left-hand side, right here, we talk about the post states for invariant 4, right? This is about the post states in invariant 1, 4. Invariant 1, 4 is here, okay? So let's now try to write them out. So let's say this is star. Star. So basically, invariant 1, 4 in the post states, okay, is going to be A prime plus B prime plus C prime equals N prime. Okay, let's put it down first, okay? And then we also got this one here, star, star. Star, star. Invariant 1, 5 is here, okay? So we got A prime equals 0 or C prime equals 0. So now we got a prime version, which is a good start. But that's not the final answer. We somehow have to do substitution to replace A, B, C, and also N. So this is why when you look at the rule, it tells you that when you try to work out the post-states version of the concrete invariance, you have to look at the effects for the abstract events, you also have to look at the effects for the concrete events. You want to look at both of them, right? That kind of tells you the hints. All right. Let's now look at the ML out right here. Okay, ML out, which has to do with this. All right. So for ML out, you can see here we got m prime equals m plus 1. M prime, m plus 1. I can do replacement right away. And I also got a prime equals a plus 1. A prime equals a plus 1. What about b prime and c prime?
No change.
No change, right? Remember the before-after predicate. This will be as if we say b prime equals b and also c prime equals c. This is where it can be useful logically. So b prime will be replaced by b, c prime here replaced by c. All right. So we already work out for this one here. I'll put it here. We basically got a plus 1 plus b plus c equals m plus 1. That's our final answer. All right? You don't really have to simplify. If you leave it like that, that's even clearer. But if you simplify, that's okay. We can accept both versions. All right? Let's now look at this one here. But this one here, because that's related to MLN, so we have to somehow do the replacement according to the before-after predicate for MLN, abstract and concrete, right? So for the abstract, we got m prime equals n minus 1. M prime equals n minus 1. So, we don't have n. Lucky, right? We don't have that. But on the other hand, we got c prime equals c minus 1. C prime equals c minus 1. So c prime, c minus 1. Whereas a prime equals a and also b prime equals b. So a prime equals a. So all we got eventually, a equals 0 and, or c minus 1 equals 0. That's the final answer, right? So final answer right here. But if you put the intermediate one here and work out along the way, I think that's reasonable. Okay. Questions? Yeah.
So you have the bottom, you said there's like 10 obligations?
Yeah.
The way to do island in, island out, too. So wouldn't it be like eventually?
So, sorry, are you asking like which 10 or?
No, as in like, wouldn't we eventually have to also do island in, island out? Because those are also like two complicated events.
Oh, you mean the new events, right? Like, yeah. So, yeah, good question. You're kind of moving ahead. I'm saying as far as MLR, MLA is concerned, when we talk about preservation, we just only got these 10. Because so far, we only try to restrict to the events that already exist in the abstract model. But starting from Thursday, we'll see some new events which don't really exist in the abstract model. They need some special treatment. Yeah. That's good. All right. All right, let's now move on a bit. All right, guys, I will leave this diagram here maybe after a short break. Okay, I think I'm almost through about what I want to achieve today, almost. Okay, let me just say something very brief, and then we'll take a short break, and then I want to finish this diagram. Okay, so these are the two proof obligation we just listed right here, one here, and also one here. Okay, the usual business, right? Maybe after the test tomorrow, maybe after Thursday over the weekend, when you want to catch up the study, you may just want to do the proof, right? Again, the solution is on the slides. Okay. And then, but you can actually blank out maybe about the relevant rules just to practice to see how you can improve them, right? They are all provable. This one here and this one here, okay? And then also very quick, okay? After invariant preservation, we also have to talk about invariant establishment. That one over there also very straightforward. That one just about having the init events. You want to make sure the post state for the concrete event can be established by the init. Pretty much like a post state established by the abstract event in the M0, like what we did earlier. That one should be straightforward, okay? So I'll leave this to you, okay? So how many proof obligations should we need? Only one single init event, but we got 5 different invariant to establish, so 5, right? So that one there should be straightforward. Okay, so this one here, we don't need to spend too much time. And these are the corresponding invariance proof obligation, some of them, 2 of them. You can give it a try. Usually invariance establishment should be very, very straightforward, almost instantaneously. You just have to apply certain small number of inference rule. Okay, I'll leave that to you. Okay, so this one here will be the new events that your fellow student just mentioned. I will talk about them maybe from Thursday, maybe not today. So the plan will be, let's take a short break for now, and then I want to finish one final diagram to link between the 2 words, and then I'll end the class today, and then I can stay a little bit longer if you got any questions, more like an extended office hour. Okay, let's take a short break. All right, so before the break, we spoke about proof obligation for invariant preservation, and also this is something I want to talk about. This one just like a conceptual diagram to show to you how you can relate about the various concepts that we have spoken about so far. I want to talk about this diagram here from scratch. It actually can give you some insight as well. Okay. This diagram here is something called commuting diagram. Okay, let me just start with the name. Okay, right. So this is the so-called commuting diagram. Conceptually, well, just overall, you can think about when you make a transition here in the abstract. Okay, sorry, let me say it again. When you make a transition by the concrete event, let's say ML out, there should be a corresponding event right here. Okay? So you can think about there are 2 ways for you to get to here. Either you can go here to here directly, or you can go to the concrete one, go here, and go there. Go there. Commuting, you can go either path. That's what commuting really means. But let's now understand this. So we talk about concrete versus abstract. Let's use the ML out, for example. So we talk about 2 transition here. So we got concrete transition, the concrete state transition. So we talk about a concrete version of ML out. And also the abstract state transition, which is also ML out. And there is a special term, simulated by, okay? So another way to phrase it more intuitively, I'll put it here. Simulated by found correspondence. 2. All right? It says the following. When I make my concrete state transition, let's say ML out, in terms of A, B, and C, I should be able to find the correspondence in the abstract model right here, the abstract state transition. Okay? So what we say is there are 2 ways for you to say this. You can either say the concrete events. Okay, let me just write it down. So we got concrete events right here. Could be ML out, for example. And also we got the corresponding abstract version of the events, also ML out. So there are 2 ways you can understand this. Either you can say the concrete is simulated by abstract. Simulated by. Or you can say the abstract one simulates the concrete, right? Just playing a little bit with the language. Simulates. Okay? So you can go either way. Either you say simulated by this direction here, or we can say simulates. Okay. Let's understand about different components here. Let's start with the concrete world. Okay. So I'll start with the left bottom corner. So here, let's start with here. H here is the concrete guard. Where the concrete guard is actually true, that means the concrete events is enabled. Do you remember Gauss strengthening? Gauss strengthening tells us if this is enabled, that implies the abstract one should be enabled as well at the same time, right? So let's now talk about that one there. The G here is the abstract events enabled. And the way we understand about the relation between these two is about guard strengthening. Guard strengthening, which is H implies G, right? Somehow related to the guard strengthening coverage earlier, right? So now at this point here, and also at this point right here, is a good starting point where both events, the both version of ML out are enabled. So we can now take that transition, okay? And you can think about here, the W is what we call a concrete pre-states, the pre-state in the concrete world. Concrete pre-states, where H is enabled. And also the V here is the abstract pre-states. Abstract pre-states, where the abstract guard is true. That means abstract event is enabled. Okay? How do we relate these two states? The linking variance, right? Right here. Okay? So think about these two are enabled, are related right here. So these two are related by the linking variance. Linking invariance, especially invariant 1,4. I think that's a label, right? All right, so now we can do transition, okay? So you can think about, we make some transition right here. So make a, okay, let me use a highlighter. I think that'll be better. So we make a concrete transition because the concrete guard is enabled. Correspondingly, we also make an abstract transition as well, right here. Okay, right here. Okay, they both terminates, and then you can see we now got two post states, right? Let's now do also annotation here. So this state here is the concrete post states, because you can see prime, right? W prime. Versus V prime over here, that is the abstract post states. To really show the correspondence between the two post states, again, we actually evaluate the linking variance in the post states. So here, let's now do that again, right here. This, again, is a linking variance. Linking invariance in the post states. And that one is a linking variance in the pre-states. Right? So overall, let me recap. Simulation tells us for refinements, every concrete transition, if enabled, there's got to be a corresponding abstract event that's also enabled and also executed because of guard strengthening. So think about when we actually talk about invariant preservation and guard strengthening, we discuss them separately. So when we talk about invariant preservation, we assume guard strengthening is the case. So when we say the concrete event is enabled, we know that by guard strengthening, the corresponding abstract event should also be enabled in the particular scenario as well, because we are not creating any new behavior, right? Whatever that's enabled in the concrete, it must be enabled as well in the abstract. And then we take the transition, and then the corresponding post states should also be consistent with respect to the linking variance. Okay? So very important diagram here, just kind of summarize and put everything together, right? About abstract concrete states, abstract concrete events, and also abstract concrete guards. Question?
So which invariant is considered as linking invariant? Is that all the invariant or only a particular invariant?
Good question. Linking invariant has, well, they don't really have a very formal definition, right? But I can write it down. But that's accurate enough, okay? So whenever we talk about, it's a good question, okay? So let me put it here. So whenever we talk about linking invariance, okay, Number one, linking invariance should be defined in the context of the concrete model, not the abstract one. Because the abstract model should not be aware of the concrete variables. Right? You can think about concrete model inherits all the abstract variable. It should be, number one, defined in the concrete model. Number two, the linking invariance should really involve both abstract and concrete variables, both. If the invariance only involves the concrete variables, in that case, very likely could be either a typing constraint or it could be a safety invariance. You're only concerned about the concrete state space. Okay? Involve both abstract and concrete variables. You might be asking, can the linking invariance, can some invariant in the concrete world only involve the abstract variables? No, because you're really supposed to involve at least the concrete variables in the concrete model. Okay? All right, just to answer about linking invariance, it's really about linking between the abstract and concrete, so both variables must be there. Okay? Does that answer your question? Yeah. Okay, good. So guys, any more questions? Okay, if that's good, so I'll stop the recording now, and then I think I will still have time, about 20 minutes. I'm happy to stay. If you got any questions, maybe give me a few minutes, I'll pack up, and then I'll answer your questions. Okay?